Sorry for the long delay there, taking a while to get everything all situated after Thanksgiving break. So you can see that today's notes 7.1 and 7.2 are actually combined together. We'll actually just cover a few pages of the notes, stop it, and then continue it on through the rest. So we'll cover these notes over the next 2 days. But we are actually moving a little bit away from probability now. So chapter 5 and 6, we spent a lot of time dealing with probabilities and different ways of calculating out different types of probability. In chapter 7, we're going to start to really focus on sampling and how we can use sampling to start to make decisions about the population. But to get us first started in chapter 7, we have a little bit of terminology that we want you to get to know and make sure you use appropriately. So the first two definitions up here are parameter and statistic. A parameter, okay, is simply a number that's going to describe some sort of characteristic about the population. So when we talk about parameters, it focuses on the population. I like to think of the letters that they both start with. Parameters go with population. So you'll see down here, you'll see me say population mean or population standard deviation, population proportion. There's going to be specific symbol notation that we use to represent parameters. So if we're talking about a population mean, we use the symbol mu. If we're talking about a population standard deviation, we'll use the lowercase sigma. And if we're talking about a population proportion, we'll talk about the letter lowercase p. So you'll see us use these symbols quite often. Your book will use them also. Now, other than a parameter, we could have what's called a statistic. Okay? A statistic is a number, but it describes a characteristic of a sample. So what I look here is S and S. The statistic starts with an S, sample starts with an S. Helps me remember, a statistic is a sample. A parameter starts with P, it goes with populations. So notice how the symbol notation changes when I talk about a sample mean. So I have X bar, sample standard deviation, lowercase s. Sample proportion, notice how you got the hat on top of the P. So that's P hat, or a sample proportion. I put these ones down because these are the ones that we will use by far the most in this course. So probably the most important thing in the beginning of chapter 7 that you need to be able to do is to be given a situation and be able to understand and identify what's your population, okay? What's the parameter, what are you measuring, okay? What's the sample, what's the statistic. So to give you some practice on these, or to show you some examples to start, and then your CFU actually has some more practice for you, we have a couple examples. So we're going to identify these 4 things: population, parameter, sample, statistic, in each of the following settings. So it says a pediatrician wants to know the 75th percentile for the distribution of heights of 10-year-old boys. Okay? So he takes a sample of 50 patients and calculates Q3 to equal 56 inches. Okay. So it doesn't matter the order in which you identify the key pieces, but you want to make sure you identify them correctly. Many students like to actually go, all right, sample of 50 patients. Well, I can go ahead and identify my sample. My sample is 50, I'm going to be a little more specific, 10-year-old boys. Whoops. Now, according to the problem, it said when she took a sample of 50 patients or 10-year-old boys here, calculated out Q3 to be 56 inches. So the statistic from the sample, Q3, was equal to 56 inches. Now I still need to talk about the population and the parameter. So the population is a description of where the sample is coming from. Okay? So the population is all 10-year-old boys. Not just the 50. The parameter is what we're trying to measure here, which we collected a statistic on the third quartile. So we'd say the third quartile for heights of 10-year-old boys. Now, the order in which you identify them doesn't matter. I tend to be very straightforward. I go population, parameters, sample, statistic, but I know that by teaching this, some students do a better job identifying what information they actually specifically give you, and then work with that to figure out all the rest of them. Okay. So, let's take a look at B. Switch colors here real quick. It says a Pew Research Center poll asked 1,102 12 to 17-year-olds in the United States if they have a cell phone. Of the respondents, 71% said yes. Right? So, if I do this in a different order, and I'm going to start with the population, what represents our entire population here? Okay, so it would be all 12 to 17-year-olds in the United States. So now we want to talk about a parameter. What are they trying to actually find? Okay, they want to find basically how many, or and specifically since they gave a percent, okay, anytime you see a percent, think proportion. Okay, so we're really trying to find the proportion. And again, the population proportion, the symbol is P, of 12 to 17-year-olds who own a cell phone. Okay, let's try this 3 times. There we go. So now, okay, our sample, how many people did they interview? Okay, 1,102 12 to 17-year-olds. I suppose in the U.S. I did forget that in the parameter part. And our statistic. What symbol should I use here? If I say the parameter is p, what should the statistic symbol be? P hat. And what does that equal? How many said yes? 71.71. You think that's too high, too low? 71%? 12 to 17-year-olds. I suppose possible not as many 12-year-olds might have a cell phone. You guys remember what age you were when you got your first cell phone? 9, 14, 13. So like when you started junior high. Okay. Someone said 9. Wow. So should I wait? How long should I wait until I get Sophie a cell phone? 16, 20, 21. Okay. So I'll let her start dating at like age 30. That's what we all say. So, all right, let's continue on. In this first part of chapter 7, we're going to have a lot of terminology. Okay. And the first couple things that we're going to talk about is this concept and what we talk about sampling variability and a sampling distribution. Okay. So, sampling variability, basically what it means is when you start to collect samples, we know that you're not always going to get the exact same result when you collect a sample. So the example here is a great way of describing it. If you flip a fair coin 50 times, would you expect everybody in the room to get exactly 25 heads? Probably not. In fact, let's do this for a second. Take out your calculators if you have them with you today. I'll turn my calculator on. And we're going to simulate flipping a coin 50 times. We imagined it, but we're actually going to simulate it. Did we simulate it before? Oh, that's right. We did it in the simulation back in what, chapter 5? Okay. So let's do it again. We'll do it pretty quick here. So, those of you who have your calculators out, so I'm going to go to my math menu. I'm going to go over to probability, and I want to choose random integer number 5.
Why don't we just use the coin simulator?
Because it takes so long.
Wait, would you click? Hold on.
Math, use the right arrow, and go over to the probability menu. Choose number 5, random integer. So, I'm going to go 1, 2, 50. So now what I can do is go ahead and hit enter, and it simulates tossing a coin 50 times if I let a 2 represent a tails and a number 1 represent a heads. So what you can do right now, I'm just kind of curious, those of you who have done it, go ahead and count the number of 1s that you have. I will do the same thing here. 6, 7, 8, 9, 10, 11, 12. Come on, it's not moving anymore. 12, 13, 14, 15, 16, 17. Come on. Wow, look at those 2s.
Wow.
18, 19, 20, 21, 22, 23, 24, 25. Wow, I actually got 25.
Wow.
Okay.
What do you have?
All right, Those of you who actually did it, I'm just curious, how many heads did you actually get? I'm just gonna go up and down. Yep. 27. Okay. No? 25? Okay. 23? Okay. If you didn't do it, it's no problem.
25.
Okay. 25? Who said, I'm sorry, I couldn't hear 25. 25? So I have 3 25s. Anybody else in this row?
25.
25? Wow. Okay. Anybody in this row? No one? Oh my goodness, you guys are all sleeping?
27.
27? I chose 1 to be heads, but in the end it wouldn't matter. 26? 27? 26? Okay. 22. 24, and another, I heard a 25, okay? So notice how we would expect to get 25, but, all right, in our 2, 4, 6, 8, 10, 12, 13 that we collected real quick, we got anywhere from a low of 22 all the way up to 27, okay? So now, if you were to continue this process for a long time, okay, in fact, forever, you would get what's called the sampling distribution, okay? It's basically all the values, okay? It's the distribution of values taken by this statistic on all possible samples of the same size. So we're flipping or simulating flipping a coin 50 times. We collected 13 samples, but in order for it to truly be a sampling distribution, we would have to continue to do this forever, okay? Forever. So basically, because we have to do it forever, it's almost impossible to collect all the possible outcomes, right? But we can start to approximate it by taking a look at a large number of samples. Like say, for instance, 100 samples, or 200 samples, or 500 samples, or 1,000 samples. And we can start to take a look at what does the distribution of coin tosses, outcomes out of 50 coin tosses, look like, okay? So, to talk about this, let's take a look at this example down here, okay? It says, if we use a statistical software to simulate 500 simple random samples of size 20 from a population of 200 chips. So in a bag we put 200, say, poker chips, where 100 of them were red and 100 of them were blue. Okay. What we did was we take out a simple sample of 20 chips, okay, and calculate out the sample proportion of red chips. Down here below is a dot plot of the results. So this is a dot plot of, okay, a simple random sample of 500 where n is equal to 20. So for instance, like this data point right here at this very end represents p hat is equal to 0.15. What that means is 15%, or in one of our samples, we only got 3 out of 20 of the chips to be red. But as you can start to see, okay, you get some interesting patterns within our sampling distribution. So the first question here, it says, A, is this the sampling distribution of p hat? Is it truly the sampling distribution? What has to be true about a sampling distribution that we talked about earlier up here? Has to be what? All possible samples. So is this truly a sampling distribution? No. No, it's an approximate sampling distribution using a total of 500 samples. Okay. In order for it to be a true sampling distribution, it has to use all. Well, you're not going to be able to collect every single sample because you can do this process over and over and over and over and over again. So, B says describe the distribution. So I'm going to shrink this a little bit so that I can still see the distribution, right, and be able to write at the same time. This goes back to our chapter 1 days. So I recall some of my terms from chapter 1. Do you guys remember the acronym from chapter 1 that we used to help us remember? It's on your feet. No. What do you put on your feet sometimes? Socks. So remember that acronym and what some of those stand for? Shape, center, spread, outliers. Oh my goodness. All right, how would you describe the shape? Yeah, I would say definitely symmetrical. Would you say it's bell-shaped? Kind of look like a normal curve? So, and bell-shaped. Are there any outliers? So that's the O, outliers. Is there any point seeming not to fit the distribution? Okay. Maybe 0.8? And how about this one here, the 0.15? Okay. So we can say maybe 0.8 and 0.15. But we're not 100% sure about that one. How about our center? Yeah. Our center, p hat, looks like it's at about 0.5. Well, that's what we would expect, right? If half of them are red and half of them are blue, we would expect the center of our sampling distribution to be right at 0.5. How about our spread? Okay. Well, we can't really calculate out standard deviation, but I suppose we can talk about spread in the general case. We can state it from the low to the high. So we could say our samples go from 0.15 to 0.80. All right, last question. Suppose your teacher prepares a bag with 200 chips and claims half of them are red. So for instance, I have a bag, you haven't seen what I put in there, and I'm telling you, 100 of them are red and 100 of them are blue. Okay, but you can't see the contents of the bag. I mix them up, and you take out or you have a classmate take out a simple random sample of 20 chips. 17 of those chips are red. What would you conclude about your teacher's claim?
Tell the truth.
The teacher's not telling the truth? You trust me? Thank you. Okay. What would you maybe suspect? That everything's all right? Okay. Well, let's think about this. 17 out of 20. What is that as a sample proportion? 0.85. So that's our p hat. How often, when we did a simulation where it actually was, did 0.85 actually occur? Up here, how often did 0.85 occur? Never. 0.85 never occurred. Do you think that's odd? Do you think that's okay? What does that make you suspect? Right? Do you believe that? Do you still believe the teacher?
Less.
You believe in the teacher a little bit less? Why is that? Okay. Well, looking at the statistical evidence, 0.85 never happened in 500 tries. Yet, one try here, it happened on the first try. Make you wonder if the teacher is telling the truth? Okay. So, let's at least note that. Okay. So, a p hat equaling a sample proportion equaling 0.85 never happened in 500 previous samples where a bag contained 100 red and 100 blue chips. This suggests the teacher may not be telling the truth. The truth. Love the truth. This is how we start to use statistics to show whether or not something might be out of the ordinary or something might be wrong. It's kind of a different type of mind thought, but with statistics, what we actually start to do is show evidence that something is false or something's not really believable. Okay? So in this case, the first student got a result that never occurred in 500 samples. Okay? Wow. Never occurred probably means that maybe something's wrong, or we just happen to get that one extreme outlier right away on the first try. Could that happen? Sure. Is it likely to happen? Probably not. And that's where we're going in Chapter 7. We're going to start to take a look at these sampling distributions and start to use them to make judgments, okay, about our population. Okay. All right, let's stop here for today.